Let's try an application word problem using calculus. The distance of a particle from a sensor can be modeled by the equation p at t equals 200 sine pi t, where p at t is the position in centimeters and t is the time in seconds. Part A. What will be the velocity of the particle at 4.3 seconds? So what we're given is the position-time equation. And if you've taken a physics course, you already know this. But if you take the derivative of a position equation, what you'll get is the velocity equation. So we can say that the velocity equation, v at t, is equal to the derivative of p at t. So how do we take the derivative of this equation here? Well, the 200 on the front is just the coefficient, so we can leave that alone. And then we have sine of something. Well, if you remember your rules for taking the derivatives of trig functions, we know the derivative of sine is cos. So we'll have cos of pi t. However, that thing in the bracket that we were originally taking sine of, that's not simply t, it's pi times t. So because of that, we have to use a chain rule. We have to multiply by the derivative of that inside part. What's the derivative of pi times t? Well, pi is just a number, and when you take the derivative of a number times t, what you'll get is that number, right? If this was 3t, you would get 3, right? Pi is just a number. We treat it exactly like we would any other number. So this is the derivative, and that means that it is also equal to your velocity. So the velocity at time t is equal to this. Fantastic. Now the question was find the velocity at 4.3 seconds. So all we have to do is plug in 4.3 into our velocity equation, and we should get our answer. So 200 times, and you can put the pi from here at the front, so it's with the other coefficient, the 200, and then cos of pi times 4.3, just like that. Now, let's solve this. If you solve this, you should get as an answer 369.32 centimeters per second. That's the velocity. Now, if you're not sure why taking the derivative of the position equation gives you the velocity equation, let's just think about it for a second in terms of an xy set of axes, or in this case, it would be a t and p axis, right? The t-axis is in seconds, and the position axis is in centimeters. And we don't know exactly what this graph looks like. We could figure it out, but I don't want to spend too much time on that. But let's say it's something like this, right? And you want to find the velocity at a point right here, right? Well, think about it. If we're taking the derivative and we're trying to find the slope of the tangent line at a point, how do we find the slope normally? Well, it's rise over run. Well, what's the rise? Well, the unit for the rise is centimeters, because on the y-axis, the p-axis, it's in centimeters. The t-axis, or what would be the x-axis normally, is in seconds. So when you find the slope and you do rise divided by run, you're doing centimeters divided by seconds, right? So centimeters over seconds, that's your velocity. That's why when you take the derivative of a position time graph, it gives you a velocity time graph. That's the reason. So let's move on to part B. Part B says, what is the particle's acceleration at this time? Well, just like how when we wanted to find the velocity, we took the derivative of the position. To find the acceleration, you take the derivative of the velocity. So let me write this out here. If you have your position at t, and you decide to take the derivative of that with respect to t, what you get is your velocity. If you decide to take the derivative of that again with respect to t, what you get is your acceleration time equation. So you can go from position to velocity to acceleration. Now, let's find the acceleration equation. We already know that the v at t equation that we found from part A is equal to 200 pi cos of pi times t. That was the equation we found. If we take the derivative of it again, that will give us the acceleration equation. So let's take the derivative of this. The 200 pi stays the same, that's your coefficient. When you take the derivative of cos, however, it becomes negative sine. So I'm going to put the negative on the front of our equation and put the sign here. So negative sine of pi times t. Now, just like the last time we took this derivative, this is not simply t, it's more complicated than t. So we have to use a chain rule. Multiply by that derivative and you get pi. Now, I have a pi here and a pi here. Instead of writing pi twice, I can simply say pi squared. So, let's now figure out what the acceleration is at this time. By this time, they're referring to the time given in part A, which was 4.3 seconds. So we can plug 4.3 into this equation. Negative 200 pi squared sine of pi times 4.3. And if you do this calculation, you should get negative 1,596.94 centimeters per second squared. Now, let's talk about these units for a second. If you've taken a physics class before, you know the units on acceleration are always a distance per time squared, just like it is here. And we can look at it in the same way we looked at part A. When you have, and I'm not going to draw out the whole curve, but if there's a point on that curve and you want to take the slope at that point, you have to do your rise over run, right? The rise in this case is what type of unit? Well, this is a velocity time graph, right? So on your y-axis here, on the v-axis, your units are in centimeters per second already. So centimeters per second are the units of your rise. The run is in seconds, right? Because on the x-axis or the t-axis, you're working in seconds. So when you find this slope, rise over run, centimeters per second divided by seconds, that gives you centimeters per second squared. That's why taking the derivative of v at t will always give you a at t. Hopefully that makes sense. Let's move on to question C. What is the maximum velocity the particle achieves, and at what times does it reach it? Well, let's think about what our velocity time graph looks like. And I'll just do a very rough sketch. So you have your time, you have your velocity, and it starts at the top and it comes down, goes to the bottom, and then it comes back up like this. Now, how do I know this is what it looks like? Well, because v at t is equal to 200 pi times cosine of pi times t. Cosine always starts at the top at the maximum and then comes down and back up. Now, I know that it's not some variation of this because while the amplitude changes and the period changes, there's no other transformations. It doesn't move vertically or horizontally. There's no shifts or anything like that, or phase shifts. So I know it's going to start at the maximum and then go down. So the maximum velocity starts at 0. So we know that right off the bat. Now, using derivatives, however, you could say that at that point, the slope of the tangent line is equal to 0. And in fact, that's true at the maximum values as well as the minimum values, right? The minimum and maximum values all have a slope of 0 when looking at their tangent lines. So if we're thinking about the derivative of this thing, so we can talk about these tangent lines, what we're really discussing is the acceleration. And we already said that the acceleration time equation is equal to negative 200 pi squared times sine of pi t. Well, in this case, if you want the rate of change to be 0, if you want to find where those maximum and minimums are, you can plug in 0 for the acceleration, right? Because 0 are the slopes of these lines. So 0 equals negative 200 pi squared sine of pi t. And if you were to solve for t in this case, divide both sides by this big coefficient, it would go away, and you'd be left with 0 equals sine of pi times t. And at this point, you could take sine inverse of both sides, but that would just give you one answer. And we know there's not one answer, right? We know that these answers repeat themselves. You reach that maximum at multiple locations. You reach that minimum at multiple locations. This is a continuous function. It keeps going to the right and to the left. And the question actually asks us for multiple answers, right? It says at what time or times does it reach this maximum? So instead of just taking sine inverse here of the other side, I'll ask myself the question, sine of what gives me 0? Well, pi t equals what? Okay, well, I know that sine of 0 is equal to 0, so pi t could equal 0. But I also know that sine of pi is equal to 0. I also know sine of 2 pi is equal to 0. I also know sine of 3 pi is equal to 0. And if you're not sure how I'm doing this, think of your unit circle, and I'll do a very crude sketch over here of that as well. If your radial arm is here at 0 radians, sine of that 0 is 0. If it rotates to over here, right, it's rotated an angle of pi, well, sine of that is also 0, right? The height of this thing is 0. If it rotates to over here, that's an angle of 2 pi radians. It's at 0 again, and that repeats itself. So whenever you have an integer times pi, like any of these answers, 0 pi, 1 pi, 2 pi, 3 pi, those will all give you a sine value of 0, meaning that you're at these maximum or minimum values. So here you have a value of 0, here you have a value of pi, here you have a value of 2 pi, and it just continues and continues. So when you look at the maximums, you can say, oh, the maximums are happening at the even ones, right? Not the odd ones. The odd values, the 1 pi, the 3 pi, etc., those are where the minimums are happening. So we want just the maximums. So the maximums for us are happening when pi t is equal to an even number times pi. In other words, t has to equal one of those even numbers. Now, how do we show that? Well, we can say t is an integer, like n, given that, now how do we say that we want n to be an even integer? Because if we just say n is an integer like this, that includes the odd numbers. Well, we can say that n divided by 2 has to be an integer. Now, why would that make sense? Because if you take an even number and divide it by 2, it becomes an integer. If you take an odd number and divide by 2, it's not an integer anymore, right? So this is a nice little trick that you can use to sort of denote that this needs to be an even number, right? So if this n is the number 2, 2 divided by 2 is 1, 1's an integer, so it makes sense, right? So this will only yield you even numbers. So that would be my answer. So to be a little more specific, if I want to give some examples of what I'm talking about, I can say that t could be 0 seconds. It could also be 2 seconds. It could also be 4 seconds. It could also be 6 seconds, etc. Right? That pattern continues. That's what this is saying. Hopefully that makes some sense. Another way that you could solve this without thinking about where all those different values are located on the graph is by taking another derivative. And you might be saying, why would I take the derivative again? Why would I take the derivative of my acceleration? Well, because if you do that, you can actually figure out whether your graph is opening up or down at those maximum and minimum values. In other words, you can figure out if a maximum or minimum is a maximum or if it's a minimum. You can get a little bit more information. So if you look at the acceleration equation, the a at t is equal to negative 200 pi squared times sine of pi t, right? So now if we want to figure out, okay, is the t value of 0 at 0 seconds, is my velocity at a maximum or is it at a minimum down here? We already know the answer. It's a maximum, right? Because we're familiar with what this shape looks like. But you might not always be familiar with what the shape looks like, right? Or you might forget. So what you can do is, after you take the derivative once and you get this, you can take the derivative again, a prime at t. Now, what happens when we do this? Well, you're going to get negative 200 pi cubed cos of pi t. Now, how do I do that so quickly? Well, you're following a pattern, right? Sine becomes cos. We know that we're going to have a chain rule multiplied by the derivative of the inside. That's going to cause this pi to increase, right? If you want to go through the long process, you can do it again and simplify, but I know you're going to get this. Now, let's plug in a value of 0. Let's find a prime at 0. Well, we're going to have negative 200 times pi cubed times cos of 0. Right? Because pi times 0 is 0. Now what is cos of 0? Well, it's equal to 1. And so what do we get here? We get negative 200 pi cubed, which I don't care what that number actually is. The point is it's a negative. And if it's a negative, that means that the graph at that point is opening downward, which means that that point is a maximum rather than a minimum. So that's how you can check. You can use what we call the double derivative. And the reason I'm calling it the double derivative is because the graph we're talking about is the velocity graph. You had to take the derivative twice of the velocity graph or the velocity equation to get to this equation here, right? We take the derivative of the velocity equation once to get acceleration, and then again to get this one. So rather than calling it a prime, I might prefer to call this v prime prime at 0, because it's showing that we took the derivative of the velocity graph twice to figure out whether the graph was opening downward or opening upward, right? If this was a positive, it means the graph would look like this at that point, and that point would be a minimum, right? That's what would happen if it was a positive answer, but it was negative, so it's this scenario, and we know that makes sense because we already talked about what the graph looks like, right? We already sketched it out. So we can confidently say that all those answers we provided are correct.